Hello everyone. So in the last lecture we have discussed about various mechanisms of physical mechanisms for realizing integrated photonic modulators, and we have also explained that this pre-carrier concentration effect actually is the most important one, and using that especially silicon photonics modulators, various types of silicon photonics modulators have been demonstrated and very much popular these days for photonic integrated circuits, particularly for optical interconnect applications. So today we continue some of the demonstrated devices. Silicon devices means silicon photonics modulators. What is their design principle, that means design parameters, and of course how they work, what sort of principles, what type of design architectures people are using, and various type of performance metrics also for silicon photonics modulators will be discussed today. So let's try to see that what are the main mechanisms used for pre-carrier concentration, for exploiting pre-carrier concentration. Okay. So first thing is that I have taken three representative cartoon figure from this paper. It was actually published in Nature Photonics in 2010 by G.T. Reed, who is actually one of the pioneer figure for silicon photonics devices and circuits. The first one is this one. So if you just carefully look into it, this is your actually Reeb waveguide structure. If you see here, this is your Reeb waveguide structure shown here, and in the slab region you see this side is actually p-type doping. P plus means it is moderately doped, and top of that you can have a metal structure so that you can make a contact with the P plus, and you can also have N plus, and you inside this is actually can be your low doped regions, and in between you can have a oxide barrier, very thin layer of oxide barrier. Okay, this is one type of structure, and then another type of structure, it is actually simply similar basically, but this thin layer of oxide is not there. This is your guided mode. It is shown with some red spot here, and here also it will be also guided mode will be there. So in this case, the only thing is that only difference is that thin layer of oxide is not there. And another type of structure, which is actually a pin type waveguide structure. So this is your waveguide, of course, and one side is p-type doped. This is a diode basically, PN diode. So p-type, P plus doping for contact, and then p-type doped, and then another one half it can be n-type doped, and then n plus you can make a contact also there. So these three different type of device architectures today used for demonstrating high-speed modulators. I will discuss one after another. First, let us concentrate on this one. That is called carrier accumulation. So this thing is called this type of waveguide structure or modulator structure. It is actually works in the principle of controlling carrier accumulation in the waveguide region. Okay. A thin insulating layer of silicon dioxide is used to isolate two halves of the waveguide to form a capacitor structure. Okay. Now, if you see this cross section a little bit more elaborately, then you can see that okay, one of the demonstrated device using this structure, it is shown here, where actually you have the silicon substrate here up to here. This is the silicon substrate, and then this is your box layer. Of course, this box layer not shown up to the scale, and this is your what you call that small layer of oxide here it will be there, but here this region is n-type doped silicon substrate. So this is a silicon substrate and then a thin layer of oxide, gate oxide, very thin layer, and then you can deposit a polysilicon. Okay, polysilicon, you know, polysilicon can be used as a gate material, gate metal, and then you can actually make a contact with a metal here, and you can apply a voltage here, and this metal contact, both sides you can actually apply voltage. So if you apply a voltage, what happens, depending on the voltage, positive or negative, you can see both sides of the gate oxide you can have charge accumulation. So one side will be positive charge, another side will be negative charge accumulation. Okay, this is something like a similar type of structure like metal oxide semiconductor structure. So if you give a bias, you can actually accumulate carriers, free carrier around this gate oxide both side, and if you withdraw the voltage, then your carrier will be removed. So as you know, in the previous lecture we have discussed, depending on the carrier concentration, refractive index can be changed, both real part and imaginary part. So in this case, these people, they exploited basically real part of the refractive index. So if you analyze the metal oxide semiconductor structure, you know that the carrier accumulation, either electron in one side and holes will be other side, positive, other side, their carrier density will be identical, and that can be expressed by this equation. What is that? Epsilon 0 r. This derivation I am not giving you because any of the solid state device book, this type of formula always will be there. If you are interested, you can just learn from there. And here I have just taken the expression directly. So epsilon 0 r, epsilon 0 is the permittivity of the free space, epsilon r is the relative permittivity or dielectric constant, and E is the electronic charge, which is nothing but 1.6 into 10 to the minus 19 coulomb, and T oxide is the oxide thickness here using this layer, oxide thickness you are using, and this T is nothing but your thickness of the what do you call that? So gate oxide layer thickness, and this is the thickness of the this T is the thickness of the okay, now I remember. Yeah, so T ox is the oxide thickness, and this T is the thickness of the layer where this charge is being accumulated. Okay, so if you have a thin oxide layer, then both sides, this side will be positive holes will be accumulated, this side will be negative accumulated, but you will get a effective thickness both sides. If that thickness is basically T, small t, then your carrier concentration is inversely proportional to that thickness, and also inversely proportional to gate oxide thickness, inversely proportional to your electronic charge, and directly proportional to the dielectric constant. And you have, this is the voltage, where Vd is the applied voltage you are giving here, either from this side to this is your Vd, you can say, with respect to the other side you can have Vd, and VFB is the so-called flat band voltage. Flat band voltage is nothing but basically work function difference between metal and semiconductor. So metal, here it is this polysilicon being used as a metal, it's a conducting layer, and semiconductor, basically this is the n-type silicon you are considering, and their work function difference is called flat band voltage. So if you can apply the bias voltage over the flat band, then you can see your carrier concentration is going to be changed, can be accumulated, carrier can be accumulated here in this thing. And you know waveguide, how it is designed, how waveguiding is happening, it is like a reef structure. You see, this is your silicon layer, and the top of it is a polysilicon. That means including polysilicon you can have your waveguide structure. So rib region is the polysilicon and bottom region is your silicon substrate. So your waveguide mode will be just like this. Here it will be confined the waveguide mode. And it has been shown that about 9% of the field distribution is penetrated into the polysilicon. Because you know polysilicon is like a metal. If it is more field is penetrated into the metal, you can experience a lot of losses. So that's why it is designed such that majority of the guided mode will lie in the silicon N type. It's a weakly doped silicon surface is there. And here a small portion you have heavily doped, so that body can be grounded, so that you whatever the voltage you are applying here with respect to the ground, and body is grounded, and these two things can be actually connected, sorted here, so that both sides you can apply voltage, and depending on the voltage, charge carrier will be accumulated here. So that amount of carrier concentration you can just find out this one. Of course, here if you see this carrier concentration is being changed, but not entire field profile of the guided mode. So that's why this effect is relatively small though, but it was the first time actually demonstrated gigahertz modulator. That means this carrier modulation, that means accumulation and non-accumulation, that speed can be very fast. You can just attract carrier and then refractive index change, and you can remove the voltage, the carrier again will be relaxed, and then your refractive index will be changed, and you can say the phase modulation. So you can use this type of structure in arms of the Mach Zehnder interferometer. For example, here it is shown 3-dimensional view. Your light is guided here, and it will be split into 50% here, 50% here, and you can have both side phase shifter, but you can utilize one of them so that, because you know there will be certain kind of losses even if even in the absence of voltage in the one of the arm. You can see that the light, when propagates directly, they will be equally attenuated, so that equal amplitude comes here and they will be constructively interfering. It will reproduce very constructive interference, light will be there. So when you go for on-off condition, that means if you are just introducing pi phase shift by changing your VD, changing your carrier concentration, that means you can get destructive interference. So your extinction will be very large. On-off extinction will be very large, because the on-off extinction to be large, it is mandatory that both the interfering wave they should be of equal amplitude. So that is the reason the phase shifter you are integrating here, and also phase shifter you are equal same phase shifter is integrated here, but you need to give voltage only in one of the arm, so that you can actually change certain kind of phase in one arm. You can get a phase difference, and phase difference you can modulate, and you can get light modulation output here. Okay, that is what we have discussed earlier, how Mach Zehnder interferometer works. So if you see that as a function of drive voltage here, drive voltage in one of the arm, I'm just discussing only this part here, carrier accumulation. You can get a carrier accumulation of this type of thing, but the structure I have shown here, this device I have shown here, that is actually first demonstrated modulator, silicon photonics modulator, using this MOS capacitor type architecture. So here if you see, as you increase the drive voltage, so because of some kind of imbalance, it is, you expect that depending on the voltage, normally as a function of voltage, it is almost proportional. Refractive index is carrier concentration variation is proportional, and we have seen from the Drude model, Sorev-Bennett model, empirical model, that refractive index is more or less proportional to the carrier concentration. So I can say that the refractive index change is proportional to the voltage, and voltage refractive index, when it is proportional to the voltage, that is fine, and also phase change also will be proportional to the voltage when lambda is fixed, lambda is constant. So in that case, your here output will be pi cos square phi, whatever the phase difference is there, pi by 2. So that means it should, as a function of phi is a voltage and it is almost linear to the voltage. So that means phi increasing means your output here, that will be varying as a cosine function, cos square function. So it is seen that it is almost like a cosine function, it is increasing, right? So as a function of voltage, you can see this one. But if you see that from maxima to minima, this is maxima to minima, you see the voltage difference is more than 8 volts, 7-8 volts or so. So that's a higher drive voltage though. But since it is a carrier accumulation and carrier deaccumulation you are creating, and in this way they could demonstrate a first gigahertz modulator in 2004. That is by Intel, of course. Intel with his advanced technology, they have demonstrated this type of modulator. Okay, so carrier accumulation, that is gone. And then they try to see that if you see normally this is, as I mentioned, that P output will be equal to P input cosine square pi by 2. Normally, if you see your modulation frequency, suppose you are giving a modulation frequency here, so, and this one it is grounded, and this may be V0 sine omega t you are giving, sine omega mt modulation frequency, and depending on that your phase will be modulated, and as the phase modulated, your light intensity will be modulated. So maxima to minima, so that means you can go constructive interference and destructive interference, constructive interference and destructive interference. How fast you are modulating them, that is decided by the modulation frequency omega m. So as you increase the frequency, modulation frequency, of course omega m is nothing but 2 pi times fm. So this is fm, for example, linear frequency. And you see that optical response means you have to see that this is a minima, and then if you are going maxima and then minima, because this is your destructive interference and this is high intensity, if you are giving that it is a high intensity and this is low intensity. This variation is actually modulation response, optical response, I would say, modulation depth. So this modulation depth, that is actually called as a optical response. So this optical response actually can vary as a function of frequency, because you can think of that as frequency is more and more, the carrier movement may not be that fast, that cannot follow that frequency. That is the reason the modulation depth or optical response is going to be changed. So that is how you say that the modulation response is slowly reducing. This is the experimental results. So at least you see that this is the normalized value, that means highest extinction, and slowly as you keep on increasing frequency, the extinction will be reducing. And this, if this is the 3 dB, this is your 3 dB, right, up to 3 dB, because of the limitation of the whatever the modulation signal of that frequency and photodetector response, etc. So they have shown up to 1 gigahertz and up to 2 gigahertz, 4 gigahertz, up to 4 gigahertz. But if you see, it could show that the bandwidth in the order of gigahertz. 3 dB bandwidth is more than 1 gigahertz. So that was the first demonstration of gigahertz modulator using FCC. That means free carrier concentration effect. By modulating carrier concentration in the guiding region, they could demonstrate gigahertz speed modulator for the first time in 2004 by Intel. Okay, so but the problem is that in this type of device, that your voltage requirement is very high. Okay, and also the length is also very important, because refractive index is changed, because you know that even if you are considering this geometry, thin layer, the carrier concentration is changing only very small region, but waveguide mode is spreaded over large distance. That's why your effective change of refractive index or overlap of the carrier concentration with the mode is very little. That's why you need a very long length of the millimeter length of the waveguide for the phase for the required phase shift. That is actually drawback for these things. But nevertheless, it showed a path that okay, if you can control the carrier effectively, then you can go for a very high speed modulator. Okay, so next they have shown also how they, for example, they have used a PRBS pseudo random bit stream they have used, and they try to see if your electrical here you are giving this signal, that means your phase shifter it is responding like that, because this may be 1, then 0, 1, 1, 1, then 0, 1, and so on. If your data streams are like this is as a function of time, right? Then according to your data stream, your phase will be modulated, and according to your phase modulation, your light intensity will be changed. They have shown that they are actually almost 1-to-1 replica you are getting. This is your electrical signal and this is your optical signal, and that is how you can say that electrical signal is converted into optical signal. So that is how you can transmit with the optical frequency. That is the role of the modulator basically. So they could reproduce up to 1 Gbps. The bandwidth is more than 1 gigahertz, and then find the optical response, optical on-off output, that is your digital data. You can encode it and encode very nicely up to 1 Gbps. So first gigabit per second transmitter, optical transmitter, they could demonstrate for the first time. Okay. Now next type of things, that is called carrier injection. So this is the model I am talking. This is B. This is the device architecture. So this is same p-type doping, n-type doping, that is fine, but no oxide layer. This region is completely intrinsic. Okay. So intrinsic means when you are not controlling carrier, you are not injecting any carrier, then light will be that means around, say, lambda equal to 1550 nanometer wavelength. So that wavelength actually it will see like a intrinsic silicon, it will be guided like a dielectric material medium. So no attenuation, nothing will happen. No refractive index, nothing will change. Now if you give a forward bias, suppose you are giving a positive to this one, this you are giving positive V0, and this maybe you are grounding or negative terminal you can connect here. Then what happens, because of the forward bias, hole will be injected this side and electron will be injected this side. So you can, by giving a forward bias, you can inject a carrier, you can enhance carrier. Both this side you can increase your electron, and from this side you can increase your hole, and you know electron and hole both can change your refractive index. Okay. So that actually demonstrated with this type of structure. For example, actual real device, when they demonstrated, you see this is the waveguide structure here, that is the intrinsic region. When light will be guided here, confined guided mode will be there. One side is the p-type doping in the top is the slightly very small thickness you have doped with a p-type material, and both side n-type doping. So these two things you can ground it, you can have one terminal, confine it, and here you can put your positive bias here. You can connect here positive bias. So you can give a positive and then you connect here, and this one can be connected with a oxide layer. It is not shown here. So in that case what happens, hole will be injected this side, and this side it will come, this side it will come, and electrons will be going from this side to this side because of the biasing condition. Okay. So in this process they could demonstrate for megahertz to gigahertz range modulation, but it could not be increased. The modulation frequency could not be increased. The reason being, you know, it is like a you are injecting carrier from this side to this side. Now when you are withdrawing your voltage, where those carriers should go? The carrier you are not again pulling back. What happens? These injected holes and electrons, they recombine. That recombination lifetime takes a time. It has its own lifetime. For a given semiconductor, if you have certain kind of carrier density for electron and hole, excess carrier you can create. That excess carrier, once it is generated, they will actually try to recombine, and it will take its own sweet time, and that time is in the order of, say, nanosecond. Okay, 10 to the power minus 9 or something. So maximum, if you want to give, suppose you want to give a digital data, for example this one. So if this data coming and you have injected carrier, now this next data you can send 0. You have to wait until those carrier you have injected, they should actually recombine. Then only your next bit can come. That is how your speed, modulator speed is limited by the carrier lifetime. Okay. Nevertheless, that was a very nice demonstration. It is also demonstrated in 2004 up to gigahertz modulator. But so far I remember in this paper, if you read, and that is Ping et al. They have actually demonstrated this device with some kind of theoretical model, and they showed that theoretically by simulation result they showed that this type of modulator can go up to gigahertz range. But again, it cannot be not beyond that. Okay. Then another type of modulator, that is actually carrier depletion. So A is actually what I said, that carrier accumulation, and this one is the carrier injection. You are injecting by forward bias, and then depending on the forward bias on off, you can actually control the carrier, you can modulate your signal. Okay. Real part of the refractive index, and you can use Mach-Zehnder interferometer. The another type of structure is you just directly make a PN junction. This is the heavily doped for contact purpose, P plus, and then lightly doped P in the order of 10 to the power 17 centimeter cube, and another half N type. So you have a junction in the semiconductor diode junction is there, just vertical to the waveguide cross section. Okay, this junction region, you know, any diode, when you make a P type and N type, so one side is, suppose this side is P type doping and this side is N type doping, then in the junction region, in the metallurgical junction region, you can see that hole will be diffused this side and electron will be diffused this side, and you can get a depletion width. And in the depletion width, normally there is no free carrier, only ions will be there. So because there is no free carrier but ions will be there, so free carrier's absence means there is no refractive index change. Now if you can just control the bias, you can just depletion region, always you know that you can have a diode, and if you give a reverse bias, suppose you are giving something, this is negative and then positive you are giving here, then what happens? If you are giving a reverse bias, this depletion region also will be increased. That is also, you can find any semiconductor device book that because of the reverse bias, your depletion width actually enhanced. Now you can increase the depletion width and you can decrease the depletion width by controlling the reverse bias voltage. So this can be your data. So you're depending on your electrical signal, that how much reverse bias you are giving, high or low, depending on that you can modulate the depletion width. Modulate the depletion width means actually you can modulate the carrier overlap with the guided mode. So free carrier overlap with the guided mode. So that way actually you can control the refractive index. Carrier concentration is changing, and the overlap also, carrier concentration is in the waveguide mode region, it is changing, then you can see some kind of phase change. So these guys, this Liu et al., they demonstrated in 2007 that Mach-Zehnder interferometer, they have used a multi-mode interference, 1:2, one input, two output. Instead of directional coupler, they have used multi-mode interference coupler, where 50% goes here and 50% goes here, and they again put a phase shifter both sides. If there is any losses because of the imaginary part of the refractive index change, identical phase shifter they fabricate, but one of the phase shifter they are giving a RF source, and they are using a load resistor because this length is sufficiently large. So it is like a transmission line, signal goes here, travels here and comes back here through a load resistance, so that any RF signal that should not be reflected back. So it's a kind of transmission line, you are just terminating with a impedance matching. Okay, so that way they have done, and they have used additional arm length. That means there is an unbalanced Mach-Zehnder interferometer. You know, in the unbalanced Mach-Zehnder interferometer we have discussed earlier, where actually we have shown that your transfer function can be also like a cosine function, right? So as a function of wavelength, you will see that the transfer function will be like this. Okay, as a function of lambda. So if you operate at a particular lambda, and then if you just change a phase, then you can see that the transfer function, that means the output will be changing high to low, high to low. That we have discussed earlier how it can be done. But that high to low, that phase change mechanism is here, is the depletion, carrier depletion. You are depleting the carrier, then you are changing, because you are reducing the carrier. That means the refractive index is increasing. That means phase is increasing in one of the arm and other arm is not. So in that case, you could actually demonstrate a very high speed modulation, and data transmission they have shown up to 25 Gbps. So this is the waveguide cross section here for this phase shifter. You see P++ doping, and they have taken a via for grounding, and this side also they have taken grounding, and central region in the top layer N-type doping and bottom layer is P-type doping. So even though it is shown like that, but here the junction is in the horizontal direction. So that means you are giving a N++, you are giving a bias here, and this two you are giving a another bias, this P-type. So you are connecting this one to negative terminal, and positive terminal you are connecting here. Okay, so that means reverse bias case is happening. Now you just give your signal somewhere here, that is your data, and this depending on the data high low voltage, actually you can control your reverse bias here, and you can control your carrier concentration in this region, which is overlapping with the guided mode. You can see your phase change, and you can see your modulation output. Okay, they could send the 25 Gbps data. Okay, so this is another type of structure they have demonstrated with a carrier depletion, that is actually ring resonator. So you know, earlier we have shown that this unbalanced Mach-Zehnder interferometer you can use wavelength selective modulator, or a ring resonator type structure also you can use as a modulator, wavelength selective lasers. So you have to, if your ring resonator having a resonance notch like this, you can use a wavelength here, operating wavelength lambda OP, and then if you tune, you can change the refractive index. If you can change the phase of the ring, this is your ring waveguide, this is your ring waveguide, this is your bus waveguide, and this is P-type doping, and this is N-type doping, and you are giving a signal here. You can give a reverse bias, then your data here. Okay, after reverse bias and data, then you can actually modulate your this thing. You can modulate here. Your when you are applying voltage, transfer function goes here, and you are not applying voltage, transfer function goes here. So if your laser operating here, that means when transfer function is here, that means you can get a high transmission, and when transfer function comes back, low transmission. So you can get an intensity modulator. Only thing is that your modulation depth it's actually wavelength. You can control. You can actually modulate a wavelength which is actually close to your resonance wavelength. So that's why we call it as a wavelength selective modulator. Okay, so that means you cannot use a wavelength somewhere here which can be modulated with this ring resonator. You need to have a wavelength which is close to the resonance, which must be closer to the resonance, so that you can tune little bit of phase shift. That means you can go for intensity modulation. So here also they have demonstrated using same carrier depletion. Earlier example we have shown Mach-Zehnder interferometer, unbalanced Mach-Zehnder interferometer, and here just micro ring resonator. Some of the structure, if you see 12 micrometer diode ring, very nicely fabricated. This is the bus waveguide, and waveguide width is about 450 nanometer. And in this region, how ring and this bus waveguide is connected. So if you are launching here, then the light will comes here, and little bit will couple, and it will be circulated, and circulated comes back here, and then you can see that modulator output. And some of the electrode structure, etc., it is shown here. Contact pads, the central region how it is doped, and the outer region how you are taking contact. Of course, there are all the process in the top. There will be oxide, you have bias and metals, everything will be there, and you can understand. If you want to learn a little more, then you can actually take a paper that is actually published by Lipson et al. I think that is published in 2007 from a Cornell group. Professor Mitchell Lipson, her group actually demonstrated this type of modulator. The beauty of this modulator is that it is very compact. It's very compact because it is 12 micron radius. If you go for this type of modulator, for example, this type of modulator, this length is in the order of some millimeter or something like that. So if you use a ring resonator, the first time they say that very small footprint micro ring resonator they have used for modulation purpose. So it was very promising, and today I must say that most of the optical interconnect transmitters and also the receiver end. For demodulator purpose, demultiplexing purpose, people are using actually micro ring resonator because of this footprint alone. And you can, although it is actually wavelength dependent, but you can use a series of micro ring resonator. Each of them can modulate each of the different colors, and you can multiplex them. So it is kind of WDM interconnect you can use for data communication, chip to chip, within chip, and also even rack to rack, etc. Those type of transmitters are nowadays available, actually commercially also available. Fine. So here the actual device, when they fabricate it, and you see that transmission characteristics, whenever you are giving different type of bias voltage here, different bias voltage, how the transfer function is changing, and their extinction is also changing, because as you give a bias, internally the waveguide, inside the waveguide, losses are actually modulated, because as I mentioned that imaginary part of the refractive index also changed, and loss is also modulated, and because of the loss modulation, your Q value also changed, and extinction also is going to be changed of the micro ring resonator. That is why you see that whenever you have the this much voltage, you have transfer function here. Now if you are just increasing the voltage, transfer function is moving in this direction, because refractive index is reducing, because you are giving a positive bias voltage, reducing this side, and as you go for reducing the voltage, then it's increasing the voltage and the forward bias, then you are actually injecting the carrier. That's why transfer function is changing. So that is just to see that how it can be tuned just by biasing, and you see the bias voltage is very small. So that is actually the advantage. When I demonstrated that when I explained the first demonstrated gigahertz speed modulator, that is accumulation type, this type of structure, right? There actually we have shown that the required voltage, this VD here, whatever voltage you are giving, that is in the order of 10 volts or so. But in this case, you can actually detune, you can modulate with a very small voltage, which is actually smaller the voltage. You can use your CMOS driver circuit with advanced technology, and high profile driver control circuit you can design, high-end driver control circuit you can design, and that will be very much useful. And indeed it is being used for transmitter, on-chip transmitter applications. Okay, now I will be discussing the last thing, that is most important, of course. Ultimately, different type of architecture, different type of mechanisms, different type of wavelength selective or Mach-Zehnder ring resonator or Mach-Zehnder type, different type of device architectures, all those type of things you are considering so far. But ultimately, at the end of the day, you have to see the performance metrics. Ultimately, you have to see that, okay, the device you are designing, that is useful, that is energy efficient, that is high speed, and yeah, all these parameters you have to think of. I have listed a few parameters here that you must, whenever you are designing a modulator, whether it is micro ring resonator based or it is Mach-Zehnder interferometer based, whether it is the phase modulator based on accumulation type carrier concentration, whether the phase modulator is based on injection type carrier modulation, or it is in the depletion type. But you have to keep in mind all these things, that your frequency bandwidth should be as high as possible. So that I have shown one characteristics here. You remember that thing? So this bandwidth, that should also operate at very high frequency. You should see that it should be flat coming like this. So it should not happen that at higher frequency your carrier is not possible to move as fast as your electrical signal, because it is after all it is a free carrier concentration you are changing, modulating. So that modulation, carrier movement, that should be actually fast enough so that you can get a high bandwidth modulator. When bandwidth is high, you can actually send your data at a faster rate. Okay, whether it is a different type of modulation format, you can use a different type of modulation format, but after all your speed, ultimate speed, depends on what is the bandwidth of your modulator. Okay, so now one thing is that, okay, then driving voltage, as I mentioned, driving voltage should not be very high, and modulation speed, of course, that actually related to the bandwidth. Modulation depth. So this modulation depth, as I mentioned, that okay, if you are just using here, suppose your laser is somewhere here, okay, this is your lambda operating, and then when you are modulating here, then the transfer function moves here, right? So then this to this it will come, right? Earlier it was output will be at this level, now it will be going up to this level. So this difference actually called modulation depth. Modulation depth is defined by, actually if I just say that modulation depth, that is actually 10 log of P max, P output max divided by P output minimum to the base 10. So that is your modulation depth. This modulation depth is should be reasonable amount. So benchmark is about 7 dB, okay, but many of the device we are showing that it can be done much more, particularly ring resonator. This modulation depth can be very high, but another thing is that important, that is the optical bandwidth. For example, if you are using ring resonator, in case of ring resonator, your wavelength should be around resonant wavelength. But if you want to use the same ring resonator for modulating another optical wavelength, that will not work. So you have to choose another resonance probably. But if you are using balanced Mach-Zehnder modulator, and if you are changing the phase by means of all these regions, accumulation, depletion, and as well as injection, everything, so in that case it can operate for the broad bandwidth. So whatever things you are designing, you have to look into that figure of merit as well. And optical insertion loss. Optical insertion loss is, suppose if you are a modulator here, and then you just see that whatever the out maximum you are getting, suppose this is your ring resonator modulator and this is your output, this is P output, this is your P input, and lambda you are making with a resonant to the ring resonator, that is fine. But whenever you are getting P out max, output max divided by P input log 10, that is actually called as a, what you call that, optical insertion loss. Optical insertion loss, okay. Optical insertion loss is P output max by P input, and you take 10 log, and modulation depth is 10 log 10 P output max by P output, both are output but maximum to minimum, that is actually modulation depth, okay. And that is actually optical insertion loss. Power consumption, that means energy per bit. Suppose you are sending 45 Gbps data, or 40 Gbps data, 40 Gbps, that is the standard sometimes, 40 Gbps data you are sending, and particularly silicon photonics, most of the time people are just targeting 25 Gbps for one channel, okay, 25 Gbps. For that you are actually, you have a driving current, driving voltage, all those type of things are there, but you have to calculate that per bit how much energy it is being consumed, per bit transmission how much energy you are sparing electrically. That is actually energy per bit. That should be as small as possible. People are making benchmark of something like that, femtojoule per bit, so couple of femtojoule per bit. It should not be more than that. So otherwise people will think that why to go for optical interconnect if it is not actually beating electrical interconnect, whatever energy required there. Because here it involves a lot of other things, not only your electrical power, your laser power, you need to you have to pump a lot of power also. But the benchmark for the electrical power loss, power per bit of transmission, it is actually it is basically calculated by this formula. Suppose you know, if you are using a, for example, depletion type or MOS type capacitor, if the capacitor value is certain value, and then your modulation peak to peak voltage is VPP, then energy per bit can be shown to be 1 by 4 CVPP square. I have taken this thing, this expression from this paper. Also, if you are interested, you can just learn. So that means if you want to reduce the energy consumption per bit of transmission, then you need the driving voltage should be as small as possible, and capacitance, that means device capacitance, whether it is a MOS capacitance or it can be a depletion diode capacitance, that should be as small as possible, so that energy consumption can be low per bit things. Okay, of course the 3 dB bandwidth, I mentioned that 3 dB bandwidth, actually it has a two component. One is that how much is the whenever you are driving, then the driving circuit you have a series resistance in the modulator and then capacitor, both things are there, and you know that RC constant actually that controls the bandwidth. And another thing is that if it is a ring resonator, you know, so you are giving a off resonance and on resonant. On resonant means light will be stored inside the cavity. Now whenever you are withdrawing, two things you need to take care: how fast your carrier is changing, carrier concentration is changing, and how fast your light stored inside the ring resonator, that is being depleted, that is being drained out. So two factor actually controls the optical bandwidth of the in the output. So this tau basically actually measures the time, relaxation time, basically depends on the Q value, quality factor of the ring resonator. So that means smaller the tau, you can actually operate fast. That means when it is stored some energy, whenever you are withdrawing the voltage or signal high to low or low to high, whatever, then the energy stored inside that should be released very fast. So you cannot get also very high Q value micro ring resonator for modulation purpose at least. If it is very high Q value, that means your tau will be as high as possible. That means it will try to store the energy longer time because loss is less. So for a high speed modulation you need low Q value. At the same time you need extinction. The resonance extinction should be as high as possible so that your modulation depth is also high. So all these parameters are very important, and after all, the last but not the least, for large scale integration your devices should be as compact as possible. Footprint should be smaller. So present day, the present generation actually, they are going for micro ring resonator where footprint is small, though it is basically wavelength selective. So but that is actually very future. You can multiplex more number of modulators, more number of ring resonators. Instead of millimeter of Mach-Zehnder interferometer length, you can have 10 microns of micro ring resonators, and you can actually integrate hundreds of them. So in this way one can get more benefit using micro ring resonator. So I want to just give some kind of overview here. I have taken from this paper. This published in Nature here. This is 2010, long back though, but this list is complete. I thought of giving you an idea. Now during last 10-11 years it has progressed a lot of advanced papers are there. You can find out some of the figure of merits demonstrated by different group. They have shown here. So for example, depletion type, some references are given in this paper 61, that is depletion of a horizontal p-n junction, Mach-Zehnder interferometer structure, footprint 10 to the power 4 micrometer square, speed achieved 30 gigabit per second, energy per bit, you see 3 into 10 to the power 4 femtojoule per second. That's a large amount of power, this Mach-Zehnder interferometer. Modulation voltage 6.5 volt, large. And then the extinction, that is very good, greater than 20 dB, and insertion loss is 7 dB. That means input to output insertion loss I have said. And modulation depth speed, that means how it is rolling out the modulation, that things is given here, 1 dB per 30 Gbps. Okay, and working spectrum, that means optical bandwidth. Optical bandwidth is very large. As I said, that Mach-Zehnder interferometer, if it is a balanced Mach-Zehnder interferometer, then bandwidth can be very wide, wider bandwidth. That means you can suppose it is designed for 1550 nanometer. That means you can actually operate from 1540 to 1560 nanometer. Up to this level you can use. And then another MZI, another device demonstrated, that is 10 to the power 4, that is actually reduced. That is footprint is reduced 10 to the power 3, but at the same time speed is also reduced 10 Gbps, and energy consumption is reduced. That is 10 to the power 4, 10 to the power 3. So as it progressed, you see this is a competition going on, who can actually design a better modulator. Okay, and here however you see the 7.6 volt, along with that some additional pulse width modulation pre-emphasis is required, and that also they have used. And again the modulation depth is 6 to 10 dB, that's good enough, and 12 dB is the insertion loss, so that's a very large amount. but not available. I think modulation depth is not actually given here, per speed actually not given here. And ring resonator, micro ring resonator, forward bias, you see the dimension reduced to just 100 micrometer square, and GBPS very large, energy per bit just reduced to 300 femtojoule per bit, voltage requirement 3.5 volt, and modulation depth 10 dB, and insertion loss very low, 0.5 dB. Okay, and some this modulation depth per speed, this is another figure of merit given, and bandwidth is very low, 0.1 nanometer. As I said, that if you are using ring resonator, you have to be restricted, very small around resonator length. So now keep on progressing ring resonator, disc resonator people used also, you see. Now the basically micro ring resonator, that is in the order of 10 to the power 2, that means micrometer square, hundreds of micrometer square. This is a little bit larger, and you see at least 10 Gbps region, and energy per bit now reduced to really femtojoule per second. That is the benchmark. People are targeting that. I think recently people demonstrated in the order of couple of femtojoule per bit actually. These are the important figure of merit, otherwise it's no way that you can actually compete with the electrical interconnect. I mean to say that how you can say that, okay, if I use so much technology, I just I want to replace electrical interconnect with the optical interconnect because of so many advantages. Ultimately practical device should give, not just theory. So these are the practical devices they are showing, and the voltage, driving voltage is again down to 2 volt, 0.5 volt. That is fantastic for CMOS driver. You can co-integrate driver electronics as well with advanced technology node, and all these parameters are coming within the range, and quite helpful, and this is the thing we can use. So with this I just close the modulator chapters. I think in next couple of lectures I will be just discussing about how hybrid integration of laser possible in silicon photonics platform for really complete so that complete both light source, modulator, photodetector, everything can be co-integrated, including driver circuits. So these are the trend, how it is silicon photonics technology or photonic integrated circuit technology is progressing. Let us wait for the next lecture. Till then, thank you very much.